All right, so last time we started this problem, and I want to finish this problem. This problem has a lot of states, and I follow the notation that's in the textbook. So we talk about states with numbers as well as letters. So state C, state D, state X, state Y. And you can see that it has a compressor stage, then an intercooler, a compressor, a regenerator, a first combustor, the first turbine or high pressure turbine stages, then another combustor, then low pressure turbines, and then it goes through. Now what we have to do is we also have to put in here, just like you have to do in your work for the design project, an imaginary heat exchanger to close the loop so that we can account for all the energy transfers and all the heat transfers. This heat exchanger is left out of the textbook illustrations, but when you want to compare the Q net and the work net of the cycle, you must account for it because there's some heat transfer to the environment. This is typically still very warm gas, and you have to cool it down to 1 in order to make the Q net for the cycle work. All right, so we're going to have work out of the first turbine, work out of the second turbine, then we have work to drive the second compressor, work to drive the first compressor, and so these are going to be negative, and the other two for the turbines are positive. You calculate the work net of the cycle, so work turbine 1 plus work turbine 2. What I'll do is I'll calculate these as positive works for the compressor, and then I have to subtract them when I deal with the work net. I know the direction of the I know the direction of the work transfer for the compressor. It's into the compressor. So I like working, like most engineers do, with positive quantities as often as possible. And then where is the Q into the cycle? Well, it's going to be into the first combustor, combustor 1, into the second combustor 2. All right. Is there any other heat transfer into the cycle? Well, we do have heat transfer out in this intercooler. And we do have heat transfer out in this other imaginary heat exchanger. But those are the 4 Qs. Did I miss any Qs anywhere? Is there any heat transfer either into or out of the working fluid, out of the cycle or into the cycle in this regenerator? No, it's really in between, in one fluid stream into the other fluid stream. Nothing with the surroundings. So in the Q net for the cycle, there's 4 things that you have to deal with. You have to deal with Q combustor 1, that's in, Q combustor 2, which is in, minus Q intercooler, minus Q of that other heat exchanger. And that'll give you Q net into the cycle. Now those have to equal, work net and Q net have to equal. When you calculate the thermal efficiency, it's the ratio of the net work divided by Q in. And when you calculate the back work ratio, it's the work that drives the compressors divided by the work that came out of the turbines. And these 2 things are kind of like the high-end metrics of the cycle, the thermal efficiency and the back work ratio. So that's a reminder of this problem. Let's go ahead and set it up. We were setting it up in Excel, and let's solve for it, okay? So it'll take me a minute, but let me turn this around. All right, so let's jump into the Excel file. I think I was right at this state last time. For the Excel, did we introduce all of our states, state 1, state C, and we're going to be isentropic, compression, and then we'll calculate state CA for actual. It's a two-step process because of the isentropic efficiency of the first compressor. And then D, etc. So you have all of these states. They're consistent with the labeling that's in the illustration in the handout I gave. And then we walked through the pressures, did we not? And so each of these pressures we're able to say, oh, it starts at 90, it's 450, then it's 1100, then it's 500, then it's 90 kilopascal for the pressures. And then I like to go and put all of the temperatures in that I know. So I know T1, I know TD, it's after the intercooler, it's cooled back down to 310. We know the maximum temperature after the combustor, 1450, and after the second combustor, it's back up to 1450 as well. Well, at this point, we're going to use variable specific heats, and we're going to then use the table, the add-in, Excel add-in that I have available for you, true. And so the syntax is you say, okay, I want to evaluate the enthalpy as a function of temperature for air. And you just have to know how this function works, but if you don't, come up and click right here, and it basically will see if there's a help file for that function. Looks like that there isn't a help file for that function, which is terrible. Well, it's right here. So it says the enthalpy in kilojoules per kilogram as a function of temperature in Kelvin. So there is a help for it, but once you figure out what's going on. And then whenever you evaluate something, you should check it. Look in the table, see if those numbers match, if they're reasonable. So the enthalpy is a function of temperature for air, and I feed it this 310, and it should come back with an enthalpy close to 310. And then if I want the PR value out of that table as a function of temperature for air, I'll feed it that temperature, and it'll come back with a 1.5546. Okay, now at this point, you say, I'm going to do isentropic compression, so the ratio of P sub R's is equal to the ratio of the physical P's. So P sub R2 is equal to P sub R1 times the ratio of the physical pressures. And there's P sub R2. If you want, you can clean up the digits a little bit. Let me see about cleaning up digits. There. Okay, now that I know P sub R, I can go and get H as a function of P sub R for air. And I'll feed it the P sub R. And I can also get T as a function of P sub R for air. Feed it P sub R. And there you go. Probably should clean up these as well. Too many digits. That should be enough digits on the H. You can always show more digits later. Then we have, we know how the isentropic performance was. Let's go ahead and say, well, what was the work that the compressor won, assuming isentropic compression, something like that. Well, what was that work? That was equal to this enthalpy minus that enthalpy. So that many kilojoules per kilogram is what's required. But we have an efficiency specified for that compressor, don't we? What was the efficiency, isentropic efficiency for the compressor? 0.75. Now, if you want, you can clean that up, make it look percent, all that. But what we want to do is we want to calculate. Let me do this. I need to move these over one, I think. There. Now I want to calculate the work, compressor 1 actual. Well, it's going to be this value divided by its efficiency. It's going to require more work. It's going to require 242 instead of 181 kilojoules per kilogram. So now that I know that, I can get this enthalpy. It's the inlet enthalpy plus the actual work per unit mass, and there you go. So now I know that exit. Now if I wanted to, I can get that actual temperature. The temperature is a function of enthalpy for air, and there is the temperature. You can see that actual temperature is higher than the isentropic temperature. Now it goes into the heat exchanger and it's cooled back down to 310. Well, once you get good with the Excel, you can sort of copy these cells down and say, you know, the formula is the same. It's going to evaluate that enthalpy at that function of temperature 310, the piece of R at that temperature. If that temperature would be 315 or 320, then those values would update automatically, but it's 310 for this problem. And then we have the same steps to go across that second compressor. So I just update the, bring those equations down and apply them. And they're all relative for the going to this cell and the relative position of the current cell. So it looks like it's all done correctly. Was I given a 75% efficiency for the second compressor? So there you go. All right, now what about state X? This is where you have to stop for a while and come back to it, because to solve for state X, I need to know what's coming in the other fluid stream from the regenerator. But I can pick up the analysis and continue at state 3. True? So at state 3, I know the temperature. Hey, I can do the enthalpy and the pressure ratio, the PR. Okay, and then I can say, oh, it's going to go from state 3 to state A through that turbine, and I'll do isentropic. Now I'm going to just do this for efficiency purposes. I'm just going to copy this formula down, or maybe I should just do it long way. Let's just say it. Okay, now, so it's going to have, you take that piece of R and multiply by the actual pressure ratio. It drops in pressure, and so the piece of R is lower. I use that piece of R to get the H. H is a function of piece of R for air. Get that piece of R, and I get the temperature. Temperature is a function of piece of R for air, and there you go. So then I say, okay, that's isentropic, so what's the work of turbine, the first turbine, isentropic? That'll be the change in the enthalpy. This is a work producing device, so it would put out almost 300 kilojoules per kilogram. The efficiency of the turbine was given to be 88%. And so let me just change that to percent, 88%. So the work turbine 1 actual, I'm not going to get as much as 300. I'll get 88% of that. I'll get 263. If I want, I can move this over by a digit or make sure I can see it. I guess that's a 0 there. Okay. And so then I can get the enthalpy. It says the inlet enthalpy minus the work extracted out. And so there's the exit enthalpy. Knowing the exit enthalpy, I can get the, I don't need the piece of R, leave it alone. I can get the temperature. Temperature is a function of enthalpy for air. Boom. All right. Then you do the same thing for the next one. Here's where I'll copy and paste a bunch. And so this is for the second turbine. And for the second turbine. And it should all be relative, and you can double check or just retype everything. Okay. All right, at this point, we have 4 as the outlet from the second turbine, which goes into the regenerator. So if you look at your illustration, you say, I have some hot fluid coming in the hot stream of the regenerator, and I want to transfer as much as possible. Well, what's the maximum that can be transferred? It's like QMAX in the regen. Well, if I took this enthalpy and transferred it all to that enthalpy, so that's the maximum possible transfer from the hot fluid stream into the cold fluid stream, because they have the same mass flow rates. but we have some regenerator effectiveness, which was for this problem 80%. Was it 80%? And so the Q actual in the regenerator isn't that many kilojoules per kilogram, but it's 80% of that. So that's the actual transfer. So from the hot stream, it's going to have a reduction in the enthalpy by 505 kilojoules per kilogram. And in the cold stream, it will have an increase by 504.6 kilojoules per kilogram. True? Are you with me or not? Okay. Well, then what we can do is we can back up and we can get that temperature, if you wanted to, as a function of enthalpy for the air for this one, as well as come up here and then you can see. How do you check to make sure it seems reasonable? Start moving things to like 100%. If it moves it to 100%, that's the same as that. True? And then we have this becomes that value, and that becomes that value. So it makes sense. Check when you code things up, make sure to check them by exploring. Oops, I put in 8,000%, 80%. There you go. Likewise, you can move these percentages for the turbine efficiencies to 100%. Does it look reasonable? And then change it back to 88%. All right. So at this point, what I need to do is I need to put in some Q's. We can put them in a couple different places, but let's do this. Q's. So one of the Q's is I need it for the first compressor, compressor 1. I need it for, I'm going to put intercooler, compressor 2. I'm going to put it for the combustor 1, the turbine 1, the combustor 2, the turbine 2, and that imaginary heat exchanger to close the loop. And I'm going to talk about the Q's in kilojoules per kilogram for each of those devices. Does that make sense? So what is the Q for the first device, which is a compressor? 0. The intercooler, well, it starts out with enthalpy C, and it goes out with enthalpy D. So that's how many kilojoules per kilogram were transferred, but not into the device. So what I'll do is I know that this is where I'm going to say I need that negative sign to indicate that it's heat transfer out of the working fluid in that device. How about the second compressor? How about the combustor? The combustor, if you look at it, goes from X to 3, does it not? And it's a heat addition, so it starts at H of X. I'm sorry, it needs to be H3 minus HX, and it's a positive amount of heat transfer into the working fluid. The turbine, nothing. Second combustor, it comes in at A and goes out at B, so H of B minus H of A. The second turbine, 0. And the hard one for a lot of students, because they forget it, it's not in the illustration, is that other heat exchanger. It comes in at Y, and it goes out at 1, but I need to, it's a negative, it's a heat transfer out, so it's H1 minus HY. And then the net for the cycle would be the sum of all of these. And let's just move the digits over a little bit, clean it up. And then what about the works? Same units, kilojoule per kilogram. For the compressor, it's a work in. You know what? We already calculated. It's right there. Because it's a work in, just put a negative sign in front. That intercooler, 0. The second combustor, is this one, not compressor, and it's a negative for work. The combustor is 0. The turbine is, this is positive work out. And we have a combustor, no work. Then we have the second turbine, and then that imaginary heat exchanger, 0. And we just say do the sum over all of those. Is it going to work? Half the time it doesn't, and then I have to go and look for my error. If Q net's not equal to work net, look for a sign error or some shift, you grab some cells wrong, okay? At this point, we can finally answer the question, what is our thermal efficiency for that cycle? Well, it's the net work out divided by the heat in, and the heat comes in the first combustor and in the second combustor, and that should be a %. And so 45.9%. What about the back work ratio, the last thing we need to calculate? The back work ratio is, well, I have 2 works that come back to drive the system. Since they're negative, I'll take the negative of them. So what goes back to drive the compressors divided by the turbine output. And so that's 46.7% back work ratio. Those are the 2 things that we were asked to solve for. If you want, you can color code them. I don't know, make it look like this, put a big box or something around it, thick box, something like that. Say this is part A, this is the answer to part B. This is how you do it with the variable specific heats, using the piece of ours because you have pressure ratios. Was it helpful? All right. Now, when you solve it for the steam, you have to get steam properties, not from this add-in that I give you off of the blackboard, but you download, right, from the other university, University of Alabama. True? Have you started on the design project? Okay, good. I'm going to go ahead and stop then on this. So now let's jump into combined cycle power plants. We've covered a lot of material. Today we need to cover combined cycle power plants and then talk also about compressible effects, gas turbines for propulsion as well. Well, these power plants are very, very popular. What's combined? Well, it's combined to have a vapor power cycle and a gas power cycle. And the primary fuel is natural gas. And they can get very high overall efficiencies, okay? So here's a basic layout. You would have a gas cycle, so maybe you would ingest fresh air, take some natural gas, you compress the fresh air, put it into the combustor, then you expand it through the gas turbine. It's still very hot. So you put it through a heat exchanger, which then boils the water, and then the water goes through a steam turbine and through a condenser and then through a pump. So you have basically a water cycle, a Rankine cycle, a vapor power cycle, as well as a gas cycle. So this is gas, this is vapor. And so you'll produce some power out of the gas turbine as well as the steam turbine. But typically there's separate generators and they make electricity and put it out to the grid. CPS, we should know a little bit about where our electricity comes from. So CPS Energy is the nation's largest municipally owned utility provider. It provides natural gas and electric service. So what does municipally owned mean? It's owned by the city of San Antonio. Okay. And you are the residents of San Antonio, and hence you own it. It's owned by the citizens. A lot of the budget for the city of San Antonio, that runs for the police and the fire and all other services comes from profits off of CPS Energy. I forget what percentage it is, but I think it's like 40% of the budget. Yes, sir.
What other cities not have a city-owned?
Houston, Dallas, Fort Worth, El Paso, Amarillo, Lubbock. Most cities do not have a municipally owned. This is rare. Austin and San Antonio in the state of Texas have municipally owned utilities, and hence they're monopolies. But if you go to Houston or Dallas, Fort Worth area, you have a choice now. They deregulated power electric providers, and so you can sign up for this provider or that provider, like phone service, right? Just think of it if you had only this was your phone provider for all your cell phones in the city of San Antonio. So anyway, it was acquired in 1942. Before that, there were some generators of local utilities, and then they started being swept up and combined nationwide in the 20s and 30s and 40s, consolidated. It serves a lot of customers. It's both electric as well as natural gas. Around the seventh largest city in the United States, so it's very unique. It is the largest municipally owned utility. So even though there's bigger cities, they don't have a municipally owned utility. Today, how do they produce the electricity? 40-some% is natural gas. That's too high I don't know why. This seems unreasonable. And coal is 28%. It's their capacity, but what they're going to do is they're going to run their nuclear plants and their coal plants, and they're going to use their natural gas plants to come online and go off and up and down. And so even though the capacity is higher, they may not be running that part of their portfolio 100% or as high a percent. Nuclear, they're running all they can because they're making good money, even though it's only 14% of the capacity. Wind, see how bloated that number looks? Do you really think 14% of our energy we use in San Antonio is wind? No, that's the rated capacity. So if it's really whipping out in West Texas where the wind is, then some days you could get up to 14% production. But all right, there's some other landfill, methane, and small solar, 1%. This is the service area. So the CPS service boundary area cuts straight along the county line between Wilson and Bexar County, and looks like just a little bit of Guadalupe is in it. Comal looks like a little bit of Comal. Looks like a little chunk of Bexar is outside of it, up by Kendall County. I don't know why. And little chunk cuts. So, but basically it's Bexar County. True. And you can see the footprint of San Antonio city limits, and it's covered there. So it's a very diverse mix again. Here is probably a better number, about 35% nuclear. The electricity used in this room last year and the year before and the year before and this year, 35%, about a third of it, is generated via nuclear power, which most students would say, what? That's a lot. A third of the electric consumption in the city of San Antonio is nuclear. Coal, another third, and then you have natural gas and some renewables. I don't know why, but that renewables seems I'm a little skeptical on that, and maybe it's true. Maybe we are now getting 15% from wind, but it just seems pretty high to me. There's more that you can read. CPS owns 40% stake in the South Texas project. And who else owns the other 60%? Well, a company that services energy in Houston area, NRG Energy. They've changed names. What is it, Reliant? And then before that, something else. Or they got bought up. And then a little bit of Austin Energy. That's the other municipally owned utility. It owns 16% of the South Texas project. They have 2 units, and they make over 1,000 megawatts of power, electric power from each of those. And they are running as often and as steady as they can be. It's best to get the plant up and running and let it run, and then you don't have all that fatigue and thermal stresses when you're shutting down and bringing it up. And you make a lot of power. Where is the South Texas project compared to Houston, compared to San Antonio, compared to Austin? And there it is. It's down, Victoria toward the coast. And so we have nice power grids that bring the electricity up and over. So that's where it's generated. There's another utility, nuclear utility in the state of Texas up at Comanche Peak Nuclear Power Plant. And I don't know exactly who owns them, but they feed into Fort Worth and the Dallas-Fort Worth Metroplex. And they are equivalent 2 units of over 1,000 megawatts each. The South Texas project's a little bigger. They have a lake down there, a man-made lake. It's over 7,000 acres lake. It's very restricted. Nobody can go on it because it's a power plant area and nuclear. But they have enough capacity to build at least 2 more units down there. And they had proposed it, but then fracking, the price of natural gas, they shelved it. It was in our newspapers and TV and et cetera, because City of San Antonio was asked to purchase and be like 40% owner of it. And it was green light, green light, green light, then red light and dead for those new units. Also, they have proposed building additional nuclear power plants, not at this site and not at that site, but actually in a site around Seguin and in that area. So there may be, in your lifetime, more power plants built in Texas that are nuclear generated. The utilities group together, and so there's an Electric Reliability Council of Texas, ERCOT. You may have heard their station when they're worried about not meeting the demand of customers. Some representative of ERCOT may come on and say, please, this is August, turn off your air conditioners or sweat a little bit and try to conserve because we're maxing out our grid. Have you heard anything like that? Yeah, they'll do that some summer days. And they manage all electricity production in this state of Texas primarily. They miss out on the Panhandle and some other areas over in here, but they cover primarily Texas. There's other regional providers which are linked together. Some of them are quite large, like in here. But essentially, it's like they're linked together and there's only a few ports to ship electricity back and forth across the boundaries. Okay. But within, it's pretty well regulated. It's managed. Well, within the ERCOT region, natural gas is 45% of electric production. And coal is 35%, nuclear is 12%, renewables like wind are 7%, and there is some slight oil or other production. So if you take a look at your region, this is our region for ERCOT, they give you a bar and they compare it with the national production. And so you can see, let's say nuclear right here. What's the comparison? Well, the nation is producing more nuclear as a fraction of electricity than the state of Texas in the ERCOT region. But the natural gas is a lot larger. It's more readily available. And the coal is smaller. The coal is smaller. Okay. We don't have as many coal plants in Texas. And we're getting fewer. There's a shift to shut down a lot of coal plants. Well, CPS Energy has continued to, or recently purchased Seguin power plant. Some of you may drive along I-10 going to Houston. You can't miss it. It's right to the right after you cross into, I'll have a map, it's right in Seguin. And they are combined cycle natural gas power plant. So there's that combined cycle. It has the Rankine and the Brayton cycle, it has a gas and a vapor power cycle, and the primary fuel is natural gas. So there's Seguin. So I-10 kicking out, and then they bumped it around years ago, I don't know, in the 60s or 70s to bypass or complete I-10 around it. And here's that bump out. And so you come across the Guadalupe River, and as you go up before you hit and turn, right there's that power plant. You can see it clearly on the side of the road. And I only grabbed this picture, which is a top-down picture of it. You're rejecting heat eventually to the atmosphere in air. And they do use some water, so it's like cooling towers. And here is a flue for the natural gas. Here are big heat exchangers in which before it goes up the flue, that warm natural gas basically boils and makes steam. And that steam is then piped and piped over into a plant over here where they have the steam turbines and the condenser. And there's another unit, there's 3 of them. I just snipped it right here. And then you have the gas turbine and the air inlet to the gas turbine. So the electricity for the natural gas is made right here. You have the electric come out to tie into the rest of the power grid. Here's a question. Well, it's natural gas. Natural gas prices have plummeted, and compared to 10 or 15 years ago, they went down a lot. So the price of the energy that you use, the coal or natural gas, oil, really affects what they build in the future. And a combined cycle plant is one that. Well, a combined cycle plant is combined in having a gas power cycle and a vapor power cycle. Typically, you burn natural gas in the gas turbines, still some hot, so you boil some water to make steam, to feed into the steam cycle to make electricity. So, isn't that it? All right. How many nuclear power plants are currently? Here you go, I'll start collecting your responses. How many nuclear power plants are currently operating in the state of Texas? Well, let's see where we're at on this, huh? So we have 4 reactors at 2 geographical sites. Okay, so there you go, very good. All right, so let's change gears a little bit and let's talk about gas turbines for aircraft propulsion or propulsion systems. Most people here in this room have flown on an airplane. How many people have never flown on an airplane? I'm curious. 1, 2, really? Okay, well, your time's coming. When it is, and especially on the first flight, it's like, I hope the engineers knew what they were doing. I really, really, really hope they knew what they were doing. And there is a great industry about both stationary gas power plants as well as jet engines and gas turbines for propulsion systems. There's a lot of engineers working in this field. It's all very highly engineered. Anyway, so what do we have strapped right here under the wing? A big old jet engine. It intakes some air, puts it through many stages of compressor stages. And you can see that the cross-sectional area is going smaller and smaller because you are compressing it. The density of the air is going higher and higher, and it doesn't need that much area. Then they go, and there's some complicated flow. Most of it doesn't go right into where the fuel is, but goes around it. But you have a combustor, and in that combustion chamber, then it's mixed with the other gases because it's so hot, so high temperature. And the key thing is the metallurgy in that first turbine stage. You can't have it so hot that it'll damage your blades and they'll fail. But that then they have some turbine stages. Usually they're on different shafts. Some of them feed the compressor. Before you'd have different turbines, and they would feed the shaft to drive the electric generator. But here, there's no power needed. This is different than a stationary gas turbine. If you put it in a tank, and there's gas turbines in tanks, okay? If you put it in a ship, there's gas turbines in ships. Then they need the shaft to drive the propeller or drive the track for the tank. But here, for a jet engine, there's no shaft to drive anything. So what you do is you just have enough to extract out to drive the compressor. And now you still have high pressure, relatively high pressure, high temperature exhaust gases. Put it through a nozzle. Now you have a nozzle. What's the purpose of the nozzle? Increase the velocity. Increase that kinetic energy. Convert from the enthalpy to kinetic energy. The kinetic energy is proportional velocity squared. Get a high velocity because you want to throw these exhaust gases out at a high velocity. What's the purpose of throwing them out at high velocity? That's a fluid stream of high linear momentum. And from fluid mechanics, basically, it's as if there needed to be some force applied in that direction on the gases to make it go, to come out with such a high linear momentum flow rate. What it is the bottom of the wing, and so the bottom of the wing feels a force in that direction, which pushes the aircraft down the runway and up into the sky. And that force is called thrust. 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 I really encourage you, check out videos. Some of them are excellent. We don't have time to show it, but they just go through different types of engines, aircraft engines. We're not going to spend a lot of time talking about turboprop. Here you would have a little shaft come back and it would drive the propeller. You could have a gas turbine with a shaft to drive a propeller, turboprop. Turbofans are very, very common. And so what you do there, I'll just give you a quick overview, is all of the air doesn't go through the compressor and then bypass and then go through the turbine. They'll have a big fan on the front, and it'll take a bunch of air and bypass the whole thing, but it'll be mixed. But that fan is being driven by shaft power coming back up by the gas turbine. And what they found, engineers found, is that it's efficient to take some shaft power, bring it up, and have a fan to really ingest and propel backward a lot of air. Also, that air then helps quiet that engine. Somebody was recently telling me, was it in this class they were flying on a recent aircraft? Was it you? Somebody was, and they said how quiet it was. What was that aircraft?
It was Sukhoi Superjet 100. It's a Russian-made.
Russian-made.
Yeah.
And I'm telling you, that is high on the priority of engineers. There's a couple classes, if you had a chance to take any classes, I think you should take classes in like corrosion. That's a great technical elective. If you had an opportunity to take a class that taught you anything about noise, it would be a good skill to have, okay? Because noise is a big consideration in machinery and in design of equipment. And for gas turbines, noise has been one. Have you ever lived near an airport? I've had to sit there. We lived under the Kelly runway, and it'd be like on the phone. All right, got an airplane coming overhead. Either hold on for a second or two or call me back. But we're not talking anymore, right? And I used to also have an apartment or a house that was in Austin, in the city of Austin, before they moved the airport out. I never knew aircraft had headlights, just like an automobile. And they had a cutoff at midnight. And so guess what happened from about 11:30 to midnight? Everybody's flying in because they used it basically as a parking lot to get out of Austin to fly up to Dallas to catch the 6 o'clock and the 7 o'clock morning flights and then fly out of the hub for American Airlines. So, but the price of real estate in that area of Austin, right under the airport, what was it, Miller Airport, basically skyrocketed when the city voted to move the airport because the property values were depressed because of the noise. And believe me, it's like I could almost touch them. And they came over. It was so close, it seemed like it. Anyway, So take a look at some of those videos. Here's a question for you. The main purpose of a jet engine is to generate Wow. 100%. Congratulations. Woohoo. First time this semester, huh? SI units for thrust are, and now we'll give you another 30 seconds. SI units for thrust are thrust is a force. True? How in the world does spitting a bunch of fluid out the back of an engine at high speed give you forward thrust? That's a great question. And that's why we have a whole class in fluid mechanics. Really. So the gas turbine for propulsion is typically set up like this. The key here is the nozzle at the back. Okay? So the nozzle at the back takes the outlet of the turbine. It's still at a pressure 4 greater than the atmospheric pressure, which is the pressure at B. And the pressure at B is equal to the inlet pressure A. So the inlet pressure to the gas turbine and the outlet pressure to the gas turbine are the same. This throws students as well as some other people for a loop. They think, hey, I've got this gas turbine like this. I can visualize it under the wing of a jet engine, under the wing of an aircraft, and somehow it ingests some air in that hole and it throws some gases out in that hole or that cross section, and they think, well, this pressure right here at the exit, that pressure B must be greater than the inlet pressure at A. But it's not. But it's not. And you can argue with a lot of people, or they can argue with you, well, how does the thing work? It's got to have a high pressure and push it up. But it's not. So the exhaust gases come straight out like that, or close enough to straight out. And the pressure there is the same. So you have the key is throwing it out at high speed. V sub B needs to be high, high, high. And so if you have the same mass flow rate, m dot through the system, I know we add a little fuel, m dot of the fuel, so the mass flow rate of the exhaust is going to be the mass flow rate of the inlet air plus the mass flow rate of the fuel, because mass is conserved. But most of the time we just neglect the mass flow rate of the fuel, and it's negligible or close enough to negligible. We have other approximations in this. So what is that forward thrust, that force called thrust? It's proportional to the mass flow rate of the fuel and the difference in the velocities. Exactly right. The velocity at the exit, or B, if you want to call it B, minus the velocity coming in. And that's the whole idea. So that gives you the right units. It gives you the right, it comes out from consideration of linear momentum, right? Linear momentum. I'm sorry, did somebody have a question?
Yes, I have a question. Why here we have a PAV called PAA, but on the bottom we have PAV more than PAA?
Oh, it's supposed to be the same. Yeah, it's not greater, it's the same. Thank you very much. Okay. Any other comments or questions? All right. Well, all you do to solve a long problem like this is that you have to be able to analyze, well, we are able to analyze all of this. You have to remind yourself how to analyze a diffuser as well as a nozzle. That's all. Okay, so for a nozzle, what do we have? We have the control volume around the nozzle. We have the inlet enthalpy at 4 plus the inlet kinetic energy at 4 equal to the exit enthalpy at 4 and the exit kinetic energy, not at 4, at B. So at B and at 4. True? Sometimes I should just ditch all these subscripts A and B and deviate from the textbook because it really is annoying. But I'm trying to stay with the textbook so it helps you. Which of these 4 groups of terms is approximately 0? H of 4, 1/2 V4 squared. H of B, or 1/2 VB squared. Here, I'll do this. Clicker question. I think that's close to 0 or negligible. That's close to 0 or negligible. That's close to 0 or negligible. Or that's close to 0 or negligible. Which term, which of these 4 terms, which one of them is close to 0 or negligible? All right, so it is B. So we want a high enthalpy. High enthalpy will allow the flow, this is negligible, to get as high a kinetic energy outlet. We want that to be high. Okay, so but how do I analyze going from this H4 to HB plus 1/2 VB squared? Because if I know HB, then I can calculate the velocity at the exit, right? So the velocity B is equal to 2 times H4 minus HB, H4 minus HB, square root. So it boils down to, if I want to do the calculation of the thrust, I need to find V sub B, I need to find HB. So how do I find that HB? Well, you recall that we have the best flow through the nozzle is S equal to a constant, isentropic. And so what you do is you say that the temperature at the exit of the nozzle divided by the temperature at the inlet to the nozzle is equal to the pressure at the exit, at the inlet to the pressure, it's the other way around. The pressure at B divided by the pressure at 4 to the K minus 1 over K. Ideal gas, isentropic flow, true? We use that same equation. We used it before. So if the pressure goes down, the temperature at B goes down. If the temperature at B goes down, then the velocity goes up. Because the enthalpy goes down, the kinetic energy, the velocity goes up. So the key equations are something like this for the isentropic expansion, or acceleration, I should say, through the nozzle, and then the conservation of energy. Same thing over here, same equations for the diffuser. All right. Let me do this. Too many files. Don't I have too many files? So there's a lot more that we can study for propulsion. I already asked that question, didn't I? Yeah, I did. Can a rocket produce a thrust in a vacuum? No clicker question. Just no. This man answered that question definitively. Goddard, you ever heard of his name? He is American rocket, modern rockets. He worked and lived in these years, and he died in August of 45. Started out in Worcester, Mass., but did a lot of testing out in New Mexico of rockets. We honor him by naming one of the NASA centers. That NASA center located in Maryland is named the Goddard Space Flight Center. He had a postage stamp done in his honor in 1964. Do you believe you could mail something for 8 cents in 1964? Yeah. You could mail something for 8 cents. And then there's this book. Anybody read the book, Rocket Man?
Just hear the music, the Rocket Man.
Rocket Man, yeah. I don't know if it was in his honor, though, the Rocket Man. But I think there's even a movie that was done. But it's a very interesting story. This is just part of that trivia. In 1920, when he was testing rockets in Massachusetts, a New York Times thing about how he believes that the rockets can reach the moon. Ha, ha, ha. And the day after that, after its front page story about Goddard's rockets, a New York Times editorial, one of the editors, entitled "A Severe Strain on Credulity," which means I don't believe it. And he said that Professor Goddard does not know the relation of action and reaction and the need to have something better than a vacuum against which to react. Of course, he only seems to lack the knowledge ladled out daily in high schools. Very cutting. He basically was not very interested in talking to a lot of media people, especially after that. And so he was a little bit of not a recluse, but I just want to do my experiments, and if they work, great. And so, yes, rockets can go through vacuum, outer space, and it's that concept of linear momentum, isn't it? All right. The speed of sound. We need to talk about compressible effects. If you take a look, you can define in general the speed of sound in a fluid as a change of pressure with respect to density holding entropy constant. It's pretty abstract, but you can work this out for air, and a lot of times we are interested in the speed of sound, not necessarily in water or even some other fluids, but air. Air behaves as an ideal gas, so you get a simple relationship, the square root of kRT, ratio of specific heats, the gas constant, and absolute temperature. This is derivation I've done before, and you can take a look at it. It's also in the textbook, so I'm just going to allude to it, say it's there. So you can get a magnitude for the speed of sound. Look at the trend. As temperature goes up, hotter, higher temperature air, what does the speed of sound do? It goes up. It goes up a little bit. Notice also it depends on K. What is K? Ratio of specific heats. And R. R is R by the molar mass. So if you change the gas at different, leave the temperature alone, but you change the gas. Let's say you change from air, which has a molar mass of around 29 kilograms per kilomole, true, 28.97. Let's say you are at a birthday party and you change it to helium. Okay, tell me a little bit about the molar mass of helium. It's 4 kilograms per kilomole, isn't it? Helium, 4. 2 neutrons, 2 protons. Okay, we'll have arm wrestling contest to see who knows what. If you have your appendices, open it up. But it's low. It's a lot lower, true? So let's say it's the same temperature. I know that the K for a monoatomic 1.67, diatomic 1.4 room temperature is not tremendously different. But the difference between like 30 and 4 is huge. So I've never seen it done, but I've heard it done where people take a helium-filled balloon and they'll draw it into their lungs and then they'll talk. Anybody? Okay. Do they sound the same? And so what you're hearing is the difference of speed of sound in that gas, the helium that's in their lungs and that's come out, right? And so I have never seen somebody do it with argon, molar mass of 40. But I suspect it would sound dramatically different. If it was squeaky high with helium, it would be bass low for argon. Okay? Okay. Or carbon dioxide, which is 44, CO2. I'm sorry?
People do it with sulfur hexafluoride. It's denser than the air we breathe.
Oh, and does it sound
Super low.
super low? There you go, confirmation. But you could do it with carbon dioxide. What's super hexafluoride? What molar mass is that? Do you know?
From what I've heard, it's about 10 times denser than air.
Okay, so it's way up there. Is that on YouTube videos?
Yeah, Jimmy Fallon does it.
Okay. Jimmy Fallon, I guess there you go. So, but you see how it changes with temperature as well as with the composition of the ideal gas. This equation does not work for water, liquid water. It works for ideal gases, square root of kRT. Now, the Mach number everybody's familiar with. It's the ratio of the speed of something in the speed of sound in the fluid. Either the fluid's moving up to that speed, so you talk about the Mach number of the flow, or some object that's in the gas traveling through the gas close to Mach number. Here's the derivation. Congratulations. You've now been exposed to the derivation. All of this you're familiar with. Subsonic, the Mach number much below 1. Typically, if you're below 3, a lot of times they'll even say the compressible effects of gases are negligible. But be careful. You can have something where it's not flowing fast, but you've compressed it, and it's very compressible. So some people think, oh, I got air flowing in this system, and over here I put it through a compressor, and now it comes out. But because the Mach number is still below 0.3, the compressible effects of the gas must be negligible. No, you just went through a compressor. You just beat it up and boosted the pressure. This is more of at constant pressure. If the pressure's not changed because of a compressor, if it's constant pressure, so to speak, in a flow system, if you're not going very fast, if you bring it to rest, the compressible effects are negligible if you're below a Mach number of 0.3. All right. And then you get sonic, transonic, supersonic, hypersonic. So if you're moving at the speed of sound, the Mach number is 1. Transonic, it's around 1. Supersonic, greater than 1. Hypersonic, much, much greater than 1. And we do have applications, a lot of engineers working in hypersonic. They even try to get aircraft to be hypersonic, although I think the last military experiment of a hypersonic aircraft failed. But someday maybe it'll be there. We already have transatlantic flights that are supersonic. I don't know if they're still flying them. They did for a number of years. Also, if you shoot something out of a barrel, usually like to get there quickly to its target, and often they come out hypersonic. Okay? So there's a lot of applications. Now, this is one thing I would encourage you to do is go slow. You say, I noticed this device, its flow is going from 1 to 2 in it. What's the area doing? The area 2 compared to the area 1. Area 1 is the inlet, area 2 is the outlet. What is it? Is the area 2 less than the area 1? Yeah, that's what's happened. What device would we call this? A nozzle, a diffuser, a turbine, a compressor? What device? It's a nozzle. It's a nozzle, right? So what about the velocity at 2 versus the velocity at 1? What we expect the velocity at the exit to be higher, true? And then you just go through the whole thing. What about the pressure at 1 versus the pressure at 2? Yeah, my computer's not writing very good right now. How about the entropy at 1 versus the entropy at 2? We would like a good nozzle. Equal, yeah. How about the temperature at 1 versus the temperature at 2? 2 greater? Okay, if you have isentropic, I know that my pen didn't work on the pressure. What about the pressure at 1 and the pressure at 2? The pressures could be equal, But typically you've got to drive it, right? Typically you've got to drive it, push it. Okay? Okay. Now, what about this temperature? And how about what about the temperature? Well, if it's isentropic, could you use the relationship that the exit temperature of the inlet temperature is equal to the exit pressure of the inlet pressure to the ratio K minus 1 over K? Could we do that? So what would the temperature do? Yeah, it would decrease, right, wouldn't it? And then that helps explain about the kinetic energy. What would the kinetic energy do? Go up. And we know that the enthalpy is proportional to the temperature. H is a function of temperature only for an ideal gas. So if the temperature went that way, it went down, then the enthalpy went down. And the sum of the enthalpy at 2 plus kinetic energy at 2 is equal to the enthalpy at 1 plus kinetic energy at 1. Is that true? Conservation of energy, true? We've studied these. This is Thermo 1. But you want to go through slowly and work through it again and make sure we understand how a subsonic, is this a nozzle? How a subsonic nozzle works. Because now we're going to go to something else, which is shocking. I'm sorry?
I have one question. Why the P1 is more than P2? Even if it's 1, it's going to be equal.
You could have them equal, but then how is the flow going to go from 1 to 2? It's a nozzle. Typically, P1 is greater than P2. At that back of that jet engine, we only want the turbine to have a modest pressure drop across it, so we have a high pressure to push it through the nozzle to get it to go out at high speed at the back of that jet engine. So no, P1 higher than P2. Okay. This is a great type of question. You have some pressure, temperature coming in. You have an exit pressure. Notice that the exit pressure is lower. It's lower. 120 is the input, 100 is the output to the nozzle. Okay. The exit area is smaller, and then you assume isentropic flow. You could use constant specific heats. It reveals the math a little easier. Just like I used that P2 over P1 to the K minus 1 over K is T2 over T1. That's the constant specific heat relationship. And you can calculate the exit temperature using this equation. True? And then you can calculate the exit speed. You go back to conservation of energy. So we would have the enthalpy inlet plus 1/2 V1 squared equal to enthalpy exit plus 1/2 V2 squared. And then we'd have, I'm going to do it slowly, V2 squared is equal to V1 squared plus H1 minus H2, which is V1 squared plus C sub P T1 minus T2. Take the square root, and there's my exit speed.
Is it 2 times H1?
You're absolutely correct. I left out that 2. Thank you very much. So this equation you're familiar with? And so you see that it goes out faster when the temperature at the exit is lower. It's colder, cooler, lower enthalpy, lower temperature at the exit, higher speed. True? And then somebody could say, I want you to calculate that exit Mach number. Okay, exit Mach number is going to be the exit speed of the gas divided by the speed of sound in the gas, which is KRT2. True? And now you see these equations, they're basic equations, and now somebody can play the game. Okay, it was 120, take it up to 180. Oh, it was 180, take it up to 200 kilopascal. It was 200 kilopascal on the pressure inlet, take it up to 400 kilopascal pressure inlet. Take it up to 500 kilopascal pressure inlet. Okay? And what you find is that you find something very interesting. So this is a data table in Excel using those equations. This is the area ratio going from fairly like area ratio, the inlet to the outlet, or the outlet is 20% of the inlet area. Or the outlet is a very small part. This is 1%, half a percent. 1% of the inlet area. See what you're doing is you're making the area difference much greater for the nozzle. And then what do we have? The inlet pressure. Let's leave the outlet pressure at 100 kilopascal. Oh, you only have a little boost. That's 110 on inlet pressure. Oh, it's 150 or 160 or 200 or 240 kilopascal, right? And then what do we do is, this is the anchor cell, don't worry about that, but we're computing the Mach number. And so in green, everywhere here is the Mach number. So it comes out at 0.41 Mach. The exit speed is 41% of the speed of sound under this area ratio and that inlet temperature. And then you see, well, if I boost the pressure, what's the trend in the Mach number? It goes up. What can you tell me about when the Mach number is greater than 1? We would call that flow supersonic. Supersonic. It's supersonic flow. Subsonic flow, supersonic flow, right? And then look, if you have a much smaller area ratio, here is the transition, and then you're supersonic. True? So you can see that there's a range of cases where you are, how do you say it? Supersonic. Okay? Does that make sense? But guess what? We lost something in the physics. We didn't take into account something in the physics. Okay, so if you go out, let me see if I have it here. Well, this is a subsonic diffuser. Let me jump to another slide, but what will happen is if you go out into the lab and you build an experiment where you're able to control that back pressure right here, or that pressure, the supply pressure, let me call it the supply pressure, and then you have it open up into this chamber here, okay? As you boost the supply pressure, what will happen is it gets something right there. It's choked flow. It gets Mach 1. And you can't go any faster unless you do something different with the geometry. Somebody says, well, make it neck down even more. Well, you're still just having a smaller area that's choked, or Mach 1 right there. Okay? So this whole range is I cannot have simply a converging nozzle, only the cross-sectional area is converging, and expect to get flow out the outlet that is supersonic. Something's missing. Okay. So now I have to jump and get to another file. So this brings us to the basics of a rocket nozzle. This is how a rocket works. If I drew a shape of a rocket and I said the shape of the rocket looks like this, you'd probably say, nah, I think the shape of the rocket needs a little kick out like that. True? True? Yeah. And so now what do we have? Well, let's talk a little bit about a rocket. We have an oxidizer and we have some fuel. And you put them together and great things happen. You have a fireball. It's high pressure, high temperature, right? And now this high pressure is needed, and this is the converging section. That's our traditional nozzle. Things are going to speed up. But if you just stop right there and you don't have that red section, it will only come out at the speed of sound, at that temperature that it comes out at. But I want it to come out at even faster. I want it to come out supersonic. Well, the math and everything else, the experimental observation is what you can do is gently expand the cross-sectional area. Professor, that's going to make it slow down. That's a diffuser. But you're feeding it Mach 1 air. You're feeding it supersonic, or you're feeding it sonic flow. In that throat, you have sonic velocity in the throat right there. And guess what you can do if you open it back up? You can get the velocity to come out even higher. You can get the speed of the chunks of gas coming out here faster than the speed of sound in that gas. This is incredible. This is mind-blowing. All right. And then the pressure will continue to drop, and at the exit you still have the lowest pressure. So the pressure in the throat will be higher than the exit pressure. There you go. What is the thrust generated by a rocket engine with the exhaust speed of 500 meters per second and a flow rate of 20 kilograms per second? I'm just going to ask that clicker question. You'll need a calculator or be able to do it in your mind. 10 newtons, 10 watts, 10 kilonewtons, 10 kilowatts, or 10 kilojoules. What is the thrust? All right, we're done, huh? So how many people said, okay, that forward thrust is a mass flow rate times a difference in velocity? Well, the inlet velocity is negligible. It's just the outlet velocity that gives it the thrust. And so it was 20 kilograms per second times 500 meters per second. Kilogram meter per second squared is a Newton. And then I look over here. I can rule out watt. I can rule out watt. I can rule out joule. It's either 10 newtons or 10 kilonewtons. True? True. What is thrust? Force, a force. Okay. So what we would like to do to improve the thrust of a rocket, and that's why they make them this way, is if this can come out really, really fast, faster than the speed of sound at that temperature for that gas, it's great for thrust. See? So you would want this velocity greater than c going out. But that means it's a supersonic nozzle, not a subsonic nozzle. So here's the derivation of how you get the relationship between the area, cross-sectional area, and the speed. And the bottom line is you see this term right here. What is that M? The Mach number. And what happens is if the Mach number is less than 1, if it's subsonic, what is the parenthesis here, positive or negative? No. Look at, if the Mach number is less than 1, the parenthesis is positive, such that this negative sign gives us what we would anticipate, what we would think would happen, is that as the area goes down, the velocity goes up because of the negative sign. But guess what happens if the Mach number is greater than 1? What's this parenthesis right here? It's negative. It switches the intuition on us. That says that if the Mach number is greater than 1, if the area goes up, the speed goes up. How did that come about? Well, it came about from a conservation of mass, energy, and isentropic property relations. It's isotropic flow through this converging, diverging nozzle. So there's the derivation. It's in the textbook, and I've done the derivation online as well. Let me just leave it at that. Okay, all the mathematical tools are there for you. So if you have subsonic flow, if you have decreasing cross-sectional area, flow in the direction of decreasing cross-sectional area, if it's isentropic, and all of these are going to be isentropic flow, it is our traditional nozzle. Things will speed up. V2 will be greater than V1. If it's subsonic and we have it increasing area, then it'll slow down. V2 will be less than V1. It'll slow down. That's a bad looking V1 there, isn't it? But if it's supersonic, if the Mach number is greater than 1, this will be a diffuser. It will slow it down. You look at it and you say, it's going to go in a smaller area. Won't it speed it up? Yeah, if it was subsonic. But because it's supersonic, it will act as a diffuser. It will slow it down. And this will make it speed up. The flow, the velocity at the exit will be greater than the velocity at the inlet. Mind-boggling. Absolutely mind-boggling. Well, you can go to the NASA website. You can see all sorts of equations where they do the same thing that we've done. So you have a converging, diverging, a CD, converging, diverging nozzle. Notice the nozzle applies for both the converging section and the diverging section, meaning that it's at the throat. It has become sonic flow. And then that diverging section, you can get it out at a higher speed. Here's the same equation. It's in our textbook, okay? All right. It's also known as a de Laval nozzle. I don't know if I pronounced that name correctly. So it's named after a person, or it's just called a converging, diverging nozzle, or same thing. But what's interesting about this Wikipedia page is they're starting to talk about not just what the flow, the Mach number does. The Mach number goes up until it hits 1 in the throat. And then in the diverging section, it's still a nozzle, and it accelerates and the Mach number becomes greater than 1. True? Or the speed goes up. The speed is going up. That's what they're showing here. So the Mach number is less than 1 on this side. It's greater than 1 there. And the Mach number is 1 at the throat. What about the temperature? Drops, because energy is still conserved, isn't it? So enthalpy plus kinetic energy is equal to a constant. What about the pressure? Well, the pressure is high, pushing it through the nozzle. And then what you exit at is typically some sort of ambient pressure. Well, let's do this. Let's study and follow. All I'm going to do is follow the discussion in the textbook here. All right. So set up an experiment where we have a chamber that can supply gas to what we call a nozzle. All right. And at this nozzle, we're just going to have it only converging in cross-sectional area. Then it opens up into a room. And that room has ability to open a valve or open a door or open a gate or control the flow out of that room. So what do we have is you have the ability to pump up this pressure, let's call it P0, some pressure to drive the flow through the nozzle. And let's say this valve is completely closed to start. Completely closed to start. All right, if it's completely closed to start, what do you think the pressure is over here? P0. What do you think the pressure is right here? P0. What's the pressure here? P0. That's a good starting spot. Let's just start there and understand that. So what we'll do is we'll plot as a function of distance. Where we're really concerned with is that section of the nozzle. See that? I didn't line it up too well. Let me try and line it up. Right in here. Okay? Okay? All right. So here is P0. And I start, and that's my first case where the valve is closed and this pressure over here is P0. I'm going to call this my PB. I think that's the notation in the textbook. So PB is equal to P0. True? My back pressure. Now, what I do is I open the valve a little. What's going to happen to PB? It'll drop a little bit. Okay. I forgot to put atmospheric pressure. Let's put atmospheric pressure right here. So if you open the valve and out here is atmospheric pressure, it can drop. But it's not going to drop all the way to, it's going to drop a little bit. So right in here, is the new back pressure. It's pretty well constant. What happens here is that exit pressure is equal to the back pressure. And then what do we have? All in here is equal to P naught. And then something happens right there. What happens? Well, the pressure drops as it goes through the nozzle. You open the valve a little more. Open that valve, what happens to this back pressure? Drops again, right? And then you go like that. See that? Somehow you're able to maintain a constant back pressure. Some machinery is back there to keep P naught constant. But then you drop some more, and let's say at this point something special is happening, because I should have also plotted. I didn't leave enough room. I got to scoot down. That's not going to look so pretty, is it? Let's plot the speed of the flow. What is the speed of the flow? The speed of the flow is going to go up, isn't it? So the first case, it was 0 at the exit. But what's the speed doing as it goes? It's going to go up, up, up. But let's say this is the speed of sound. It hits the speed of sound, such that at this case right here at the exit, the velocity is equal to the speed of sound. If I open up that valve a little more, what will I get? Is I'll get a shock. What do you mean by shock? That means the flow in this section of the converging nozzle won't change. It'll be where it is able to provide the exit is at Mach 1. But right after the exit, there's a shock. What's a shock, Professor? Well, it's an abrupt change in the flow condition across it, such that it's highly irreversible, and you have in this case, a pressure drop across that shock, because the pressure coming out jumps to a low pressure, and there it goes. It's an abrupt change in pressure. And so you can continue to decrease that back pressure by opening the valve a little more, till it gets down to atmospheric pressure. But what you did is you increase the strength of that shock. All right. Let's plot the mass flow rate. And what happens is we'll plot it as a function of the supply pressure to the back pressure. And as if you're at 1, there was no flow. But as you drop it a little bit, the flow went up dramatically. I got this wrong. It's back pressure divided by the supply pressure. And then as you drop the back pressure some more, the flow goes up again, but then it does something like that. What's that? You don't get any more flow out of it. The flow is choked at the throat. The flow is choked at the exit. So afterward, you'll have a shock, but that doesn't help you increase the exit speed or the mass flow rate through that nozzle, does it? Not at all. Okay? Sorry? Okay, what about these shocks? There's more you can read about them, but they're a discontinuity in the entropy. It's a highly irreversible zone that's modeled as being just a planar surface. It can have curve to it, or it can be a normal shock, which is flat, or oblique shocks are different shapes. Here is just a quick look at high pressure. You have exit nozzle, you have some oblique shocks. I don't know anything about all this, and I can't explain it in 15 minutes either. But if you look at some back of engines out of exhaust, you can see some diamond shapes indicating the type of shocks that are being created in flow. So if you want to improve or increase the flow, you have to add a converging diverging nozzle. So play the same game. put something that can supply a constant pressure P naught, have a converging section, but then also have a diverging section, and then have it exit into a chamber in which you can control the back pressure. Here, you want to plot the pressure as a function of location as you drop that back pressure starting at P naught. So you start to drop it, drop it, drop it, and the flow, first of all, will simply have acceleration through the nozzle part, and then deceleration and pressure recovery in the subsonic diffuser until you're able to drop it such that you get choked flow in the throat. And at that point, you can continue to drop the back pressure. It'll start to get flow that will be faster through the section. I should do this. There's a right away, if you don't have it drop enough, it'll move out and you'll get a shock in this part or in that part, and then you can walk that shock out by continuing to decrease the back pressure here. So it'll start to drop, but then it'll jump if there's a shock in this case, and then act as a subsonic diffuser, or come out, have a shock, subsonic diffuser, supersonic nozzle all the way out to here, and then bring it all the way out. And now I have, at the exit, I could have supersonic flow right there. All right, I need to move on. And what they're doing is showing how the different back pressures, or the ambient back pressure, affects the shocks. Here are some of the key equations. This equation shows how the area change in the nozzle affects the velocity, and m is the Mach number, so it changes if it's subsonic or supersonic. What is this? This is how the temperature changes. So you talk about the stagnation temperature, the temperature of the feed. You could think about where it's not flowing with negligible speed, and as the Mach number goes up, then the temperature changes. Okay, so this is a relationship on the energy, and then also the pressure. All right, let's take a look at this equation. For isentropic flow in a supersonic converging diverging nozzle, temperature T is always less than T naught. That's the physical temperature T is always less than the stagnation temperature T. All right, just rearrange this equation. Put T naught is equal to, or here, do it this way. The temperature of interest is equal to the stagnation temperature divided by 1 plus K minus 1 divided by 2 Mach squared. All right, the Mach number, what does it range between? Negative infinity and positive infinity? No, the Mach number ranges between 0 and positive infinity, right? You can't have a Mach number less than 1. But you can have a Mach number you can't have it less than 0, but you can have it less than 1. Okay, so this equation works with a Mach number of 0.1 or 1.1. So anyway, you square it. That's going to be positive. What about K? Is K less than, can K be less than 1? You have to know that, no, K is the ratio of specific heats. No, it's 1.4-ish, 1 point something-ish. It's greater than 1. C sub P is always greater than C sub V, always. Ideal gas, always. All right, so all of this is now positive, and it's greater than 1. It's 1 plus something. So the temperature is always less than the stagnation temperature. It's always less than the stagnation temperature. All right, how about this one? For isentropic flow in a supersonic converging diverging nozzle, P is always less than the stagnation pressure P naught. Well, same type of discussion for this one. why is it, why do so many people say false? Just rearrange that equation. So P would be equal to P naught divided by 1 plus K minus 1 over 2 Mach squared to this power K over K minus 1. Now, this is positive, that's positive, this is all above positive, that's all positive, isn't it? It's all greater than 1. So its answer is A. The derivation of those equations are in the textbook. But what I need to do is I need to, great, 5 minutes. I know, how many people have seen the textbook where in table 9.2 they've taken this equation and plotted it? Or not plotted it, put it in the table. That equation, put it in the table, and this equation, put it in the table, because sometimes equations don't reveal the underlying trends. And this is with a Mach number of 1. And so the temperature will be 83% of the stagnation temperature. The pressure will be 53% of the stagnation pressure. And that area compared to the throat area is 1, because that's what A star is, the throat area. Okay. This number right here, I wish I had more time, but I'll do the best I have, is an important number because you can answer questions like this. I have a converging nozzle. It's supplied with a temperature and pressure, and there's an exit pressure. Forget about the exit area, that's okay. Determine the mass flow rate through that nozzle. And I had a question like this on the last exam, and students forgot to do something. They forgot to check, and they would come in with a speed here, which was maybe, it was definitely greater than the speed of sound. Can I have exiting a converging only nozzle flow greater than the speed of sound? No, you can't. What will happen is it'll have a shock after that nozzle. And this ratio of pressures right here tells me that to get to Mach 1, the pressure in the throat, if it's roughly equal to, I'm going to say 0.528 of P naught, if you put it lower than that, you just have a shock. And so, if let's say I'm supply 400 kilopascal here, and it's 300 kilopascal at the exit. What happens if I would put 500 kilopascal, 600 kilopascal? Well, eventually what's going to happen is it'll be choked. You can't force any more through it. The mass flow rate will be maxed out. But the equations, if you don't know it, you just go and forget about the shocks and all that. You can predict, oh yeah, you can run the equations and the Mach number will be like 2.2 or something on the exit. Or the exit speed will be 2.2 times the speed of sound at the exit. Can't happen. The students failed to check to see if it was choked. Right? So once you find that it's, what you do to find that it's choked is, if this back pressure is greater than the exit pressure divided by 0.528. A lot of people just round that off. It's a half. So when you have the supply pressure 2 times the exit pressure, if that supply pressure is greater than 2 times the exit pressure, guess what? It's choke flow. Could I ever experience and hear choke flow or see choke flow, maybe in a lab that I have, the thermal fluids lab? A lot of times they'll have an airline and they'll have a little hand-operated valve on that airline. True? And a lot of times it's just to rotate 90 degrees. If it's not too large of a line and it doesn't drop the pressure too much in the back, that pressure is very high. It'll be a 90 psi line or something like that, and you'll be add 15 so you know that it's an atmospheric 105 psi line. You're dumping it to 15 psi here. All I need is a back pressure about 2. I need a 30 psi absolute or a 15 psi gauge on the back side of that valve. I open it wide open, and you can hear it. It'll make a lot of noise, and it'll be choke flow. That's assuming that it's roughly fairly smooth. If you start having some perturbations inside, and it's not going to be near isentropic flow in the converging section, but it's a fairly good approximation. So a lot of times people will see that this number, it's like a half or 2. It comes straight out of the equations here. Okay. Anybody ever done that? Ever open a line on an air compressor system and it's very loud, and you can even have it a small section where outlets, small cross-sectional area, it'll be choke flow. Okay? Thank you very much for your attention. Yeah.